Hi guys, today I'm going to prove something really cool for you. So, see this integral here, from 0 to 1 of ln x divided by 1 plus x dx. Well, it turns out that this is actually equal to negative pi squared over 12. And I'll walk through this with you and show you exactly how you can get this. So, first thing we're going to do is integrate by parts. We'll set u equals ln x and v equals 1 over 1 plus x. So this will give us, for our du, we'll get 1 over x, and our dv will have ln of 1 plus x. Alright? And now using our integration by parts formula, which you should know, integral of u dv equals uv minus integral of v du. Right? What we'll get is the following. Let me erase this first. It's equal to ln x times ln 1 plus x. This is from 0 to 1 minus integral from 0 to 1 of ln 1 plus x divided by x dx. And now it doesn't really look like we've done that much. I mean, we have this term over here, which doesn't seem very useful to us. But other than that, the integral seems pretty similar, and it's not really completely clear immediately how exactly we're going to resolve this. So first, let's take a look at this term here, alright? Now, you can't really just say that this goes to 0 trivially, because it's not really trivial that it goes to 0. In fact, in order to determine this, we'll have to use L'Hopital's rule a couple times. But I'll leave that as an exercise to the viewer. Just start by, I'll tell you what you should do is you should start by doing lim as h approaches 0 of this here. This is, this is going to be, the one part is going to be pretty easy. This is just ln of 1 times ln of 2, which is going to be just 0. And then you'll subtract ln, and this is where the 0 comes in, h times ln 1 plus h. And if the viewer wants, obviously this goes to 0, right? Because ln 1 is 0. But the challenge here is to prove that this is equal to 0, right? But I'll leave that to you. It takes a couple iterations of L'Hopital's rule, and I'd rather not do it in this video. So now, assuming that we've proven that this is equal to 0, it's here. What we have left is negative integral from 0 to 1 of ln of 1 plus x over x dx, right? So now let's work with this. First, let's rewrite this using a u substitution to make it look a little bit better. Alright, what we'll do is we'll let u equal negative x, and that'll give us du equals negative dx, right? Derivative of negative x is negative 1. And that will give us the following, alright? So we're starting out with this. We're plugging in negative u for x, so we get negative integral from 0 to 1 of ln 1 minus u over negative u, and then here du is negative dx, right? So negative dx, negative du if we flip this around and then substitute into our dx, right? So this will be equal to what? Well, these negatives cancel, alright? And then it turns out that these bounds are actually incorrect, right? If u is or sorry, if x is 1, then u is -1, and if x is 0, then u is 0. So really, these bounds are 0 to -1, right? But we want to switch that, because we don't really want to integrate backwards. And as you know, if we flip the bounds, then we get the negative of that. So what we'll do is we'll go from -1 to 0, and that'll cancel out this negative, right? So now all we have left is ln 1 minus u over u. Alright? And this is du. So that's pretty nice. Now, what are we going to do with this? Now that we've finally gotten it into this form, what are we actually going to do with it? Well, recall the formula for geometric series, right? 1 over 1 minus x equals 1 plus x squared plus x cubed, and so on. But this is, note this only holds for absolute value of x less than 1. So this will be very useful to us. What we're actually going to do is we're going to integrate it. So if we take the integral of both sides, right? Then what do we actually get? Dx. Well, we get negative ln 1 minus x on this side. And you would do absolute value of 1 minus x, but we know that the absolute value of x is less than 1. So we can just leave this in parentheses here. And then we get here, on this side, we get this integral of this series. Well, if we integrate it term by term, we get x plus x squared over 2 plus x cubed over 3, and so on, right? And that's what we have for that result. But then we also have to add our constant of integration, and this will be the constant of integration for both. But we don't really want this constant of integration. And so what we can do is we can actually just get rid of and so how we'll do that is we'll let x equal 0, and then we'll just plug in, right? So negative ln 1 minus 0 equals 0 plus 0 squared over 2 plus etc. Plus c. And pretty quickly you can see that this is just equal to 0 and 0 plus c, which means that c has to equal 0. So we can just get rid of that constant of integration right there. And so that tells us what? Well, that tells us that negative ln of 1 minus x is equal to this series up here, right? Which is just the following sum. Sum from what? Sum from n equals 1 to infinity of x to the n over n. And so now we can actually substitute this back into our integral up here. Note that we have an ln 1 minus u. So here, we'll substitute in. And so in substituting in, let's just rewrite our original integral, negative 1 to 0, of ln 1 minus u. And this is over u, right? And then substitute in. And we get, well, see there's this negative here, so we'll have to negate the integral. So, negative integral from negative 1 to 0 of this sum here, n equals 1 to infinity, of xn, actually this should be u to the n, right? Doesn't really matter what the integration variable is here. This is over u du. And really quickly, we can notice that this u down here and this u up here, these two, will end up canceling a little bit. So if we cancel these, this will become u to the n minus 1. And so now we can rewrite this, noting that the integral of the series is the same thing as the series of the integral, as negative sum from n equals 1 to infinity of, well, integral from negative 1 to 0 of u to the n minus 1 over n d. Alright, so now we've done most of the heavy lifting. All that's left to do is kind of plug and chug. So here we go. This is going to be equal to sum from n equals 1 to infinity, and this is just n over n squared, right? By the property of the inverse power rule integral property, and then we'll have this from -1 to 0, which is just equal to, well, we know if we plug in 0, we'll just get 0, right, for the entire thing. Same as above when we integrated the geometric series. So what we'll do here is what we have left is this n equals 1 to infinity of -1 to the n over n squared. And so, well, actually, sorry, this is going to be positive because we have the 0, right, minus 1, and it's actually minus the -1, right, from these bounds. So that's what that would imply, and since this is the term that we subtract, we're subtracting the negative, and we actually get a positive. So hopefully that wasn't too confusing, right? And now what we actually want to do is increase this -1 exponent by 1. And so what I mean by that is we'll say this is equal to negative sum from n equals 1 to infinity of -1 to the n plus 1 over n squared. And the reason we're doing this will become apparent later. But basically, we don't want to have to deal with annoying partial sums that will make it hard for us to understand exactly what we want to do here. So, alright. So here we have our sum. And you may notice, this actually looks pretty similar to another sum that you should know, which is the following. Sum from n equals 1 to infinity of 1 over n squared is equal to pi squared over 6. And this is something that you may know, you may not know, but it's a pretty well-known result in mathematics, and I recommend you look up a proof of that if you find that interesting. So what we're first going to do in order to kind of realize how these two are related is write out the partial sums for this sum. And so let's do that. I'll omit the negative for now, but we'll bring it back later. So here, we'll write out the sums. Okay? So here we have 1 over 1 minus 1 over 4 plus 1 over 9 minus 1 over 16 plus 1 over 25. And that goes on like that. And so we can realize that these terms are negative for even n, right? So here, you know, this is n equals 1, n equals 2, etc. 3, 4, 5. You get the idea, right? So here, n is 2, and it's negative. Here, n is 4, and it's negative. So it's negative for even n. And what we can do is we can actually write this as a difference between two series. We can write this as a difference between this series, which we've already seen, and then some other series which only includes even n. And so the way we'll do that is we'll write it as follows, right? So we have this negative sum from n equals 1 to infinity of 1, sorry, this is -1 to the n plus 1 over n squared. And we'll actually write this as this sum like this, right? So sum from n equals 1 to infinity of 1 over n squared, which we know to be pi squared over 6, right? And what we'll do is we'll subtract 2 of each of the even terms. So this is n equals 1 to infinity of 1 over 2n squared. And these terms, if you want to write out the partial sum, are actually 2 times 1 to the 4th plus 1 over 16 plus 1 over 36 and so on, right? And so it should be obvious that if you subtract this from this sum, from this sum up here, sum of 1 over n squared, where all of these are positive, you'll actually get them to become negative instead, which is exactly what we have in this here sum. And so that is why these are exactly the same, right? And now we'll actually start solving and plugging in what we know. So we know that this is equal to pi squared over 6. So let's write that out. This is pi squared over 6 and minus, and what we'll do is we'll actually take out the 2's from the denominator here, right? So this is going to be 2 times 1 over 4, and then we're literally left with just this thing again. So 2 times 1 over 4 times pi squared over 6. And now, for the big finale, we get this to be equal to pi squared over 6 minus, and we can do the math. This is 4 and 6 is 24, times 2 is 12. So then we get pi squared over 12, and this overall is equal to negative pi squared over 12. And there we go. So, sorry if I messed some stuff up or was a little bit unclear, but I thought this was a very interesting problem. And lots of work to get this integral into a workable format. But now we know that this is indeed equal to negative pi squared over 12. So, right, if you like that, plenty of other videos of mine that would be probably generated very soon. That would be good to watch, and see you next time.